Hi everybody, today's learning target for this video is I can describe isotopes and use them to calculate atomic mass. So we're going to be talking about isotopes a lot today and how those work. We have briefly mentioned those in the past and today we're going to really dive into them. So isotopes, there's a definition up here. It says atoms with identical atomic numbers but different mass numbers, or different numbers of neutrons, okay? What I like to say is that they're different, oh, that's a weird pen, different versions, okay? It's like different versions of the same element, all right? Because they have the same atomic number or the same number of protons, right? It's always gonna be carbon or whatever you're talking about. But they're different versions of carbon because they have different numbers of neutrons, which results in a different mass because the mass is the protons plus the neutrons, okay? So for example, if we look down here, we have hydrogen in this picture, and over on the left side over here, we have just your standard everyday hydrogen, one proton, no neutrons and one electron, okay? Ordinary, this is what we find most of the time. Sometimes we have heavy hydrogen or deuterium, and that's one proton, one neutron, and one electron, okay? So it has this extra neutron, so the mass is going to be different. The mass is now 2 instead of 1 in our symbol down there, okay? And then sometimes we get tritium, which is radioactive hydrogen, and that's when we have 2 neutrons in that hydrogen. And sometimes when we add neutrons or with different ratios of neutrons to protons, we get something that's less stable, and so that's why this one is radioactive. It's not as stable with these 2 neutrons, so it's going to try to get rid of them. What that means is that we can find each type of hydrogen in the world at different times, but what really is the case is that there's usually always a super or most abundant version of each element. So we have this most abundant version of hydrogen. That means most of the time, if we have hydrogen in front of us, it's going to be this type of hydrogen, okay? But some of the time, we might have this type of hydrogen or version of hydrogen in front of us. And then more rarely, but still, we can find this version of hydrogen on the right, okay? So that's what isotopes are. They're different versions of the same element. And what's different is that number of neutrons. There's always going to be 1 or 2 that are more stable than the others. So when we're thinking about isotopes, it's kind of this abstract idea that you could have different versions of the same thing. So I like to use this pasta analogy, okay? If you look on this page, right, you have like a ton of different types of penne here, right? And overall, they like have this similar shape, maybe. They're related, right? But in between each one, you can find various differences, okay? Differences in their structure, their makeup, okay? And what we're saying is like, this is like the different versions of hydrogen. And what's different between them is minor, but it definitely affects the way that they look and the way they taste and behave, okay? All right, so let's talk more about how isotopes or different isotopes are affecting mass. So we've talked a lot about atomic mass versus mass number, all right? So remember, those things aren't the same. Mass number is a whole number. Mass number equals protons plus neutrons. So for each isotope, we can get a mass number that's a whole number. Atomic mass is going to be an average of all the different types of carbon or hydrogen that we're finding on the Earth, okay? And more specifically, it's not just a regular old average where you add them all up and divide by the number of things that you added together. This one's going to be a weighted average because I told you earlier, with hydrogen, we find that this is our most common version of hydrogen. Most of the time when you have hydrogen, you have this mass, okay? And so when we're talking about making an atomic mass, we want to give that type of hydrogen the most common or most abundant, we say. We want to make that mass closest to the average, okay? And so we weight it. We give it more weight when we calculate the average. So the definition here for atomic mass is a weighted average of the isotopic masses of an element's naturally occurring isotopes, okay? So we take each of the different isotopes, find their mass, and then we calculate a weighted average based on their abundance. Okay, so down here it says chlorine has 2 isotopes, chlorine 35 and chlorine 37. How can we determine the atomic mass? Well, we don't have enough information here. Usually we would say 35 plus 37 divided by 2 equals 36, right? Right in the middle. But we find that chlorine 35 is a lot more common than chlorine 37. So our weighted average mass, our atomic mass that we actually get, is much, much closer to 35 than 36. And then down here, just talking units, okay? AMU we've talked about briefly. We give 1 AMU or atomic mass unit per 1 proton or per 1 neutron. Remember that electrons are really, really tiny. They don't have a lot of mass, and so we do not use them in this calculation, okay? So 1 proton is 1 atomic mass unit. 1 neutron is 1 atomic mass unit. And then 1 electron is like barely anything, almost 0. It's so small, okay? All right, so let's practice here. It says rubidium has 2 common isotopes, so 2 different versions of rubidium. And what's different about them is their mass, and that's caused by a change in the number of neutrons. Remember, we can't change the protons, or that would change the identity or the fact that it's rubidium. Okay, so it says we have rubidium 85 and rubidium 87. It says if the abundance of rubidium 85 is 72.2% and the abundance of rubidium 87 is 27.8%, what is the average atomic mass of rubidium? Okay, so the information we have is the 85 and 87. Those are our 2 masses. And then we have this abundance information. Usually, when we take an average, we would just take the 2 masses, add them together, divide by 2. So it was 2 things added together. And we'd get 86 AMU for the average. Okay, but that's incorrect. We need a weighted average that takes into account the fact that most of the time when we're finding rubidium 85. So our average with the weight taken into account, our weighted average needs to be closer to 85 than it was to 86, okay? Or than it was to 87. All right, so how we do that? You're going to take the percent abundance of each one and multiply it by the mass of that one. So simple as 85 times 0.722 for the 72% over here, plus 87 times 0.278, all right? The weights, you guys, these percentages of abundance are already taking into account the part of the whole that these represent, so you don't need to do any divide by 2 at the bottom. The percentages are taking care of that math already. You don't have to do what you would normally do in an average, okay? It's almost like if in our original average calculation, instead of dividing the whole thing by 2, we did 85 times 0.5, like as if it was 50%, plus 87 times 0.5, as if it was 50% of our average, okay? As if we were dividing each by 2, all right? So the percentages, when we change them into decimals like this, we don't need to divide at the bottom at all, all right? We can just take the masses and multiply by their abundance. Remember, though, to move that decimal point if it's a percentage, because that's a part out of 100, okay? Last step is just to type that one in. You can probably get that on your own, but I'll give you a second here to type it in. All right, hopefully you got 85.556, all right? And then what unit we're gonna have here, remember, we have AMU, okay, atomic mass units, all right? That means on average, between the protons and the neutrons, they usually add up to about 85, okay? But because we have this other existing mass of 87 that is somewhat abundant, we have to factor that in, okay? Notice that our final answer, this 85.556, is closer to 85, closer to this rubidium, than it is to the 87 rubidium. And that's because this 85 is more abundant than the other. So that's what it should be. You can always do that check at the end to make sure that you are closer to your more abundant version of an element. All right. Hopefully this helps you with isotopes, gives you a little bit of background.